In 2022, the James Webb Space Telescope aimed at a patch of sky smaller than a grain of sand held at arm's length. What it captured inside? Over 25,000 galaxies, each one containing hundreds of billions of stars. We assume we grasp how large the universe truly is, but the math says otherwise. Today, you and I travel from our galaxy to the absolute edge of the observable cosmos. We encounter galaxies that existed before they should have. We map a supercluster 500 million light-years wide. We stand at the threshold of voids that physics struggles to explain. If this moves you, like and subscribe. It means everything. Now breathe. We begin. In July of 2022, NASA released an image that stopped scientists cold. It had been captured by the James Webb Space Telescope, the most powerful observatory ever built. The image covered a patch of sky smaller than a grain of sand held at arm's length. That tiny, almost laughably small slice of darkness contained over 25,000 galaxies. 25,000? Each one of them a collection of hundreds of billions of stars, some spiraling, some colliding, some so ancient that the light we received had been traveling toward us since before our planet existed. Here is what made it stranger. The telescope captured all of that in just 12.5 hours. The Hubble Space Telescope, which had transformed astronomy for decades, needed 11 full days to reach a comparable depth. Webb did it in half a day. And what it found in that tiny slice of sky forced astronomers to reconsider everything. Now hold this thought. The visible sky can be divided into roughly 540 million such grain of sand patches. If every single one hides galaxies at the same density, the numbers stop making sense to the human brain almost immediately, but they are real. This is confirmed. That image was part of a survey called Cosmos Webb. When that first snapshot was taken, it represented only 4% of the planned total. 4%. Astronomers had barely scratched the surface, and the result was already rewriting expectations. Caitlin Casey, an astronomer at the University of Texas at Austin, put it plainly. "When it is finished," she said, "this deep field will be astoundingly large and overwhelmingly beautiful." Think about what that means personally. Every one of those 25,000 galaxies has been sitting in that patch of sky your entire life. Every night you stepped outside and looked up, they were there, invisible, waiting. Your naked eye can only reach a fraction of a percent of the distance to the nearest of those galaxies. The James Webb Space Telescope extended our reach into depths we had never touched. The telescope was pointing at a cluster of galaxies roughly 4.6 billion light-years away. That cluster acts as a natural gravitational lens, bending and magnifying the light of even older galaxies sitting far behind it. Some of those magnified galaxies formed when the universe was so young that stars were still rare, fragile, newly born. What a single photograph did was extraordinary. In 12.5 hours, Webb showed us more of the universe's layered history than decades of previous observation had managed. Stars forming, galaxies colliding, light stretched so far across space that it arrived as infrared, completely invisible to human eyes, detectable only by instruments. We had always suspected the universe held more than we could see, but suspected and confirmed are two entirely different things. What Webb confirmed was overwhelming. That grain of sand patch holds more islands of stars than there are grains of sand on a large beach. If the universe looks like this in every direction, and all evidence confirms it does, then the total number of galaxies surrounding us is far beyond any prior estimate. The question was, how many? That answer had already arrived, years before Webb launched, and when it did, it multiplied the previous count by 10. For most of the 20th century, the official estimate for the number of galaxies in the observable universe sat between 100 billion and 200 billion. Staggering already. But scientists believed they had a rough handle on the total. Then in October of 2016, a team led by Professor Christopher Consolis at the University of Nottingham published a paper that quietly dismantled that assumption. They spent years converting Hubble deep space images into three-dimensional maps. They measured galaxy density at different distances across cosmic time, calculated how many galaxies were too faint or too small for even Hubble to detect, and extrapolated the full count. The result was definitive. The observable universe contains at least 2 trillion galaxies, 10 times more than previously estimated. 2 trillion. Consolis described the reaction plainly. "It boggles the mind," he said, "that over 90% of the galaxies in the universe have yet to be studied. Who knows what interesting properties we will find when we discover them?" That last sentence carries a specific weight. Of those 2 trillion, our best telescopes can currently see around 200 billion, roughly 10%. The other 1.8 trillion exist right now, confirmed by the mathematics of cosmic density, invisible to us only because they are too faint, too distant, or too small for current instruments to resolve. They are there. They contain stars. They almost certainly contain planets. We simply cannot reach them with what we have built so far. Here is why this matters beyond the sheer size of the number. Every cosmological estimate you have ever heard was built on a baseline that was off by a factor of 10. The universe was always this full. We were just not looking deeply enough to see it. Now consider the math at the new scale. If each of those 2 trillion galaxies contains an average of 200 billion stars, the total number of stars in the observable universe reaches something around 400 sextillion. That is a 4 followed by 23 zeros. No human process of visualization can hold that figure. It is beyond the ceiling of imagination. And here is something worth holding alongside that number. These 2 trillion galaxies are not evenly distributed through time. In the early universe, there were actually 10 times more galaxies per unit of volume than there are today. Early galaxies were smaller, more chaotic, more numerous. Over billions of years, they collided, merged, and swallowed each other into larger, calmer structures. What we observe today is the result of 13.8 billion years of consolidation. The original count was even higher. Think about what it means that 90% of the universe's galaxies remain completely uncharted. Astronomers estimate that each of those hidden galaxies contains its own stars, its own potential for planets, its own history. We have catalogs of everything humanity has ever explored in space, every probe, every telescope image, every confirmed discovery. And all of that combined represents 1/10 of what actually fills the observable universe. The rest is waiting. Every one of those galaxies, ancient or present, nearby or impossibly far, is built of light that has been traveling across a stretching, expanding universe for a very long time. And the next part of this story pushes that light back to its absolute limit, to just 290 million years after the beginning of everything. Because what the James Webb Space Telescope found there should not have existed. In May of 2024, a team of astronomers announced that Webb had confirmed the most distant galaxy ever observed. The catalog name is not important. What matters is what it reveals about the early universe. This galaxy existed just 290 million years after the Big Bang. To understand why that is staggering, think about what the universe looked like at that moment. It was mostly hydrogen and helium, still hot and dense and chaotic. Stars had only recently begun to form for the first time. Galaxies, the large organized structures we recognize today, had no business existing yet. Structure formation requires time. Gravity needs generations of stellar evolution to build something so complex. And yet there it was, confirmed by spectroscopy, a galaxy already tens of thousands of light years across, glowing in a universe barely old enough to have stars. The light from that galaxy left its source 13.5 billion years ago. At that point, Earth did not exist. Our solar system had not formed. The gas that would one day collapse into our star was still drifting freely through space. That light crossed the entire span of cosmic history and arrived at Webb's mirror just a few years ago. Kevin Hainline from the University of Arizona described the finding this way: "We really should not have found a galaxy like this. he said, given our understanding of the way the universe has evolved. That phrase carries weight. This is a confirmed spectroscopic observation from one of the most precise instruments ever built, and it is telling us that our models of early galaxy formation are missing something important. In early 2025, a second ancient galaxy made headlines. Published in the journal Nature, it formed just 330 million years after the Big Bang. This one glowed with a type of light called Lyman alpha emission, which should have been completely blocked at that era. The early universe was filled with a thick fog of neutral hydrogen that traps this specific light. For it to escape meant the fog around that galaxy had already cleared. But clearing that fog should have taken hundreds of millions of years more. Roberto Maiolino from the University of Cambridge described the reaction simply. This result, he said, was totally unexpected by theories of early galaxy formation and has caught astronomers by surprise. The picture emerging here is clear. The early universe was more active, more structured, and more aggressive in galaxy formation than our best models predicted. Galaxies appeared earlier. They grew faster. Something in those first few 100 million years is still not understood. And this matters beyond academic curiosity. Our models of the universe, the ones that predict its fate and describe its structure, are built on assumptions about how fast galaxies formed and grew. If those assumptions are off, the whole framework needs adjusting. Astronomers are actively revising it now, using every image Webb sends back. Each new confirmation of an early galaxy reshapes the timeline we thought we understood, which brings a problem with distance itself that most people never hear about. Because if you tried to look up how far away these ancient galaxies actually are, the numbers would not add up. They cannot, unless you understand something deeply strange about how space and time relate to each other. Here is the puzzle. The universe is 13.8 billion years old. Light travels at just under 186,000 miles per second, the fastest anything can move. In theory, the farthest any light could have traveled is 13.8 billion light years, so that should be the edge of the observable universe. It is not. The edge of the observable universe sits 46.5 billion light years away. In every direction, that forms a sphere 93 billion light years across. And this does not break physics. It reveals something about the nature of space that is even stranger than the size itself. The Big Bang was not an explosion of matter through pre-existing space. Space itself expanded. The universe did not grow into something outside itself. The distances between everything grew larger as the fabric of space stretched, and that stretching has never stopped. When the oldest light in the observable universe was first released, about 380,000 years after the Big Bang, the region that emitted it was far closer to us than it is today. While that light spent billions of years traveling toward us, the universe kept expanding behind it. The source kept being carried further away. By the time the light arrived, the region it came from had been moved to a current distance of 46.5 billion light years. This is confirmed by multiple independent measurement methods. The numbers agree. Think of it like throwing a ball across a river while the river is widening. The ball travels at a fixed speed, but the far bank keeps moving away as the ball is in flight. The ball still reaches you. But the point it came from is now much farther than when it was thrown. That is what light does crossing an expanding universe. The ratio is worth sitting with. The edge of the observable universe is currently 3.4 times farther away than the age of the universe alone would suggest. Every second you sit here, the most distant things we can observe are being pushed further away by ongoing expansion. There is a number attached to this expansion. For every 3.2 million light-years of distance, galaxies are receding from us at about 43 miles per second faster. A galaxy 1 billion light-years away is moving away at roughly 13,000 miles per second. A galaxy 10 billion light-years away is receding at a significant fraction of the speed of light. And beyond about 18 billion light-years, the recession speed exceeds light speed entirely, not because those galaxies are moving through space faster than light, but because the space between us and them is expanding faster than light can cross it. Those galaxies are gone. Their light will never reach us. Already, the vast majority of the universe, confirmed estimates suggest around 94% of it, is beyond any possible contact, and that boundary is shrinking, very slowly, every year. The force driving that expansion is called dark energy. It will return later in this story in a far more unsettling context. For now, the important thing to carry forward is this. The observable universe is a sphere 93 billion light-years across. That is the field we are working in. And before we go further out, we need to understand where we are standing inside it, because there is one comparison, a simple one, that makes the entire scale visible at once. Picture a matchstick, about 1.5 inches long, thin and unremarkable. Now imagine that matchstick is the Milky Way galaxy, the entire thing. Every star in it, every cloud of gas, every nebula, every black hole, every planet, all of it, from edge to edge, compressed into 1.5 inches. At that same scale, the observable universe would be a sphere with a radius of about 1.3 miles. One matchstick, 1.3 miles. That is the ratio between our home galaxy and everything we can observe. The scale factor is roughly 1 to 450 billion. 180,000 light-years compressed by 450 billion gives approximately 1.5 inches. This is confirmed by direct calculation. Now think about what that means in practice. Those 2 trillion galaxies we discussed at this scale would each be about the size of a matchstick. All 2 trillion of them scattered through a sphere you could run across in about half an hour. Each matchstick would be separated from the next by roughly 5 to 10 feet of empty air, mostly empty, gaps of darkness between each island. The universe is sparse, even at the scale of galaxies. If you wanted to travel from our matchstick to the nearest other large galaxy, Andromeda, at this scale, that trip would be about 6.5 feet. But in real terms, it is 2.5 million light-years, about 15 million trillion miles. And this entire matchstick universe, every galaxy, every cluster, all of it within the 1.3-mile sphere, represents only the portion of space we can actually see. The total universe almost certainly extends far beyond that sphere. How far beyond is a question for later. There is something else to notice at this scale. If you lined up those 2 trillion matchstick galaxies and spread them evenly across that 1.3-mile sphere, the average distance between neighboring matchsticks would be roughly 5 to 10 feet of empty air. The universe is mostly nothing. Even at the scale of galaxies, the dominant feature of the cosmos is emptiness. Galaxy clusters are dense knots. Between them, vast dark stretches contain almost nothing for hundreds of millions of light-years. You are standing inside one of those matchsticks right now. Every ocean, every mountain range, every city, every person who has ever lived is within the boundaries of 1.5 inches of that scale. Everything else is separation, distance, silence. But before we explore what lies in those gaps, we need to look closely at our matchstick, because even at this reduced, almost invisible scale, what it contains is already beyond the mind's ability to fully picture. There is one more thing worth extracting from this comparison before we move on. At this scale, the nearest individual star to our solar system, Proxima Centauri, which sits about 4 light-years away in real terms, would be about 1/5 of a millimeter from us, almost touching. And yet, even at that vanishingly close distance on this scale, no human spacecraft has ever come close to reaching it. The fastest probes we have launched would take tens of thousands of years to cross that 1/5 of a millimeter. The Milky Way, which looks like a small, simple thing at this scale, contains over 200 billion stars. And what that number actually means, when you try to feel it rather than just state it, is already enough to break something in how you understand size. 200 billion stars in the Milky Way, at the lower estimate. Some calculations suggest the number is closer to 400 billion, once you account for the dense stellar population hidden in the galactic core by thick clouds of gas and dust. Here is one way to make that number physical. If you counted 1 star per second, without sleeping, without pausing, you would finish between 6,000 and 12,000 years from now. Every civilization that currently exists on Earth would have risen and collapsed multiple times over before you reached the last star. The entire span of recorded history would play out again and again in the background while you counted. Our galaxy contains a range of stellar types. Most of them are small, dim red dwarfs, stars that burn slowly and steadily and can live for tens of billions of years. Some are massive, brilliant blue giants that exhaust their fuel in just a few million years and then explode. Our own star is middle-aged, stable, and positioned about 26,000 light-years from the galactic center. At that center, confirmed by 3 decades of direct observation, sits a supermassive black hole called Sagittarius A star. Its mass is approximately 4 million times the mass of our star. Teams of astronomers tracked individual stars orbiting it at high speed for over 30 years, tracing precise paths around an invisible point, and confirmed its presence beyond any reasonable doubt. This is established science. The light we receive from the galactic center tonight left its source 26,000 years ago. When that light began its journey, humans on Earth were in the middle of the last ice age, painting caves, crossing land bridges, with no written language and no permanent settlements. Our solar system is orbiting that center right now, along with everything else in the galaxy. One complete orbit takes between 225 million and 250 million years. The last time our solar system completed a full lap, dinosaurs were still early in their time on Earth. Over the full lifetime of our galaxy, the solar system has completed roughly 60 of these orbits. We have been going around this circuit before the first fish developed lungs. The speed we are traveling is roughly 514,000 miles per hour. That is extraordinary by any human standard. A spacecraft moving at that speed could reach the moon in about 28 minutes. And yet, at that speed, a single galactic orbit still takes 250 million years. And every star you have ever seen with your naked eye, every constellation familiar since childhood, is part of this structure. The most distant star visible without a telescope sits a few thousand light-years away, still well within the Milky Way, still inside that 1.5-inch matchstick. Everything beyond is a different galaxy. And beyond our galaxy, just a small distance away on cosmic scales, the first neighbors appear. Dozens of them, bound to us by gravity, forming a small community drifting together through space. Every star you know, every one that has a name, every one that appears in the mythology of any civilization that has ever existed on Earth, is inside our galaxy. All of human skywatching, from the earliest astronomers to the first telescopes, was only ever looking at stars within this single structure. We had no idea there were others until about 100 years ago. That is how recently our understanding of our own position in the universe fundamentally changed. But one of those neighbor galaxies is on a collision course with us, and the timeline is already locked in. The Milky Way belongs to a collection of galaxies called the Local Group. It contains over 50 members, though most are small dwarf galaxies orbiting the 2 largest, our galaxy and the Andromeda Galaxy. The Local Group stretches about 10 million light-years from edge to edge. That is 100 times the diameter of the Milky Way itself. Mostly empty space, dotted with dozens of gravitationally bound islands. Andromeda sits 2.5 million light-years from here. The light you see from it tonight left its source 2.5 million years ago, when our ancestors were early hominids on the African savanna, before fire, before language, before any tool more sophisticated than a stone. That ancient light is arriving at your eyes right now. Andromeda contains roughly 1 trillion stars, likely more than the Milky Way, and it is coming toward us. This is confirmed. Both galaxies are approaching each other at roughly 70 miles per second. In about 4.5 billion years, they will begin to collide and merge. The merger will unfold over hundreds of millions of years. Individual stars are so widely spaced that very few will directly impact each other, but the gravitational forces will be immense. Both galaxies will be torn apart and reshaped into a new combined structure, sometimes called Milkomeda. Gas clouds will be compressed, triggering intense waves of new star formation. Stars will be flung to new orbits far from their original positions. What emerges will look nothing like either galaxy does today. The science here is settled. The approaching velocities are measured. The timeline is confirmed by orbital mechanics. It will happen. Our solar system will very likely survive the merger intact. The odds of a direct star-to-star collision are extremely low, given how much empty space separates individual stars. But our position in the merged galaxy will change dramatically. Current simulations suggest our solar system could be thrown outward to a much larger orbit, or even into the extended outer halo of the new structure. From that vantage point, the night sky would look completely different. The familiar spiral arms would be gone, replaced by the diffuse glow of an elliptical galaxy still settling from the collision. There is also the Triangulum galaxy, roughly 2.7 million light-years away, smaller than either Andromeda or the Milky Way, but still home to tens of billions of stars. Beyond it, over 50 smaller dwarf galaxies complete the local group, most of them satellites orbiting the larger members. Together, bound by gravity, these galaxies drift through space as a unit. And as a unit, they are falling. Pulled toward a dense concentration of galaxies 54 million light-years away. A city of over 1,000 galaxies where, almost a century ago, one scientist noticed that something invisible and enormous was hiding in plain sight. The local group itself is moving through space at about 1.4 million miles per hour relative to the cosmic microwave background. That is the radiation left over from the Big Bang, which fills the entire universe and serves as the closest thing we have to a fixed reference frame. Relative to it, our entire island chain of galaxies, everything in it, every star, every planet, every atom of matter we have ever touched, is hurtling through space at speeds that dwarf anything ever built by human hands. What that scientist found, studying a cluster not unlike the one we are falling toward, would reshape our entire understanding of what the universe is made of. 54 million light-years from here, a dense city of galaxies waits. It is called the Virgo cluster. Over 1,300 galaxies crowd this region, most of them small dwarf systems orbiting a concentrated inner core. At that core sit several of the largest galaxies we have ever catalogued. Massive elliptical structures bloated from billions of years of absorbing smaller galaxies one by one. The Virgo cluster anchors the gravitational landscape of our local universe. The Milky Way, the local group, and all nearby galaxy clusters are slowly falling toward it. This is confirmed by precise velocity measurements made over decades. The pull is real and ongoing, and it has been shaping the motion of our galaxy for billions of years. But the Virgo cluster matters most in this story for what it helped reveal about something invisible. In 1933, a Swiss astronomer named Fritz Zwicky was studying a different dense city of galaxies called the Coma cluster, located about 320 million light-years from Earth, containing roughly 1,000 galaxies. Zwicky measured how fast the galaxies inside it were moving relative to each other. He then calculated how fast they should be moving, based entirely on the visible mass present. The numbers did not match. At all. The galaxies were moving far too fast. The visible matter in the cluster, all those stars, all that gas, provided nowhere near enough gravity to hold them together at those speeds. Something else was there. Something with enormous mass and gravitational pull. Something that emitted no light and interacted with nothing except through gravity. Zwicky called it dark matter. He published his findings, and the scientific community largely ignored him for decades. The idea was too strange. Invisible matter, making up most of the mass in a galaxy cluster, seemed like an unwarranted leap. His methods were questioned. The concept sat at the fringe of serious discussion for nearly 40 years. When independent researchers finally revisited the evidence in the 1970s, using completely different methods, including tracing how fast stars orbit the outer edges of spiral galaxies, they found the same problem everywhere they looked. Something invisible and massive was present in every galaxy they studied. Zwicky had been right, and the implications were larger than anyone had anticipated, because if dark matter is real, then everything we have ever seen with a telescope represents only a fraction of what actually exists. Later research added more weight to Zwicky's original claim. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford measured how far stars orbit the outer edges of spiral galaxies. Stars far from the center should be moving slower, just as the outer planets of our solar system move more slowly than the inner ones. They do not. Stars at the extreme edges of galaxies orbit just as fast as stars closer in, sometimes faster. The only explanation that fits is that an enormous invisible mass extends far beyond the visible edges of every galaxy we can see, providing extra gravitational pull across the entire structure. This invisible mass has never been directly detected by any instrument. Not one particle of dark matter has ever been captured in a laboratory. Its identity remains, as of 2026, completely unknown. The Virgo cluster, the Coma cluster, and every structure we have discussed so far are embedded in a vast, invisible scaffold we are only beginning to map. And in 2014, astronomers traced that scaffold to draw the largest confirmed structure our galaxy has ever been shown to belong to. For most of the 20th century, the local supercluster, a loose collection of galaxy groups spanning roughly 100 million light-years, was considered the largest structure our galaxy was part of. It seemed like the ceiling of our cosmic address. In 2014, that ceiling was demolished. A team led by Brent Tully at the University of Hawaii built something new, a map based entirely on motion. They tracked the peculiar velocities of about 8,000 galaxies, the small deviations from the general expansion of the universe that reveal the gravitational pull of surrounding mass. By tracing where those velocities were pointing, they mapped the edges of the gravitational basin that holds our region of the universe together. They named it Laniakea. The word comes from Hawaiian and means immense heaven. Laniakea spans 520 million light-years across. It contains at least 100,000 galaxies distributed across 300 to 500 clusters and groups. Its total mass is approximately 100 quadrillion times the mass of our star. This is confirmed, published in the journal Nature, and verified by multiple subsequent studies using independent datasets. The Milky Way sits near the outer edge of Laniakea, nowhere near its center. Flowing toward the center from our position, following the gravitational current, like water following a slope, are hundreds of thousands of galaxies. That center is a region astronomers call the Great Attractor. It lies approximately 220 million light-years away in the direction of the Norma galaxy cluster. For decades, it was hidden behind the dense gas and dust of our own galaxy's plane, making it nearly impossible to observe directly. When astronomers finally mapped around this obscuring region using different wavelengths, they found an enormous concentration of mass, drawing everything in its vicinity toward it. Our galaxy is part of that infill. It has been for billions of years. Tully described the principle clearly. Just as rivers flow within watersheds, galaxies flow within cosmic basins of attraction. Laniakea is the watershed our galaxy lives in. But here is something worth noting about our position within it. We are near the outer rim. We are on the edge of a supercluster so large that light takes over 1 billion years to cross it, and we live near the boundary, not at the center. In cosmic terms, we are in the suburbs. The dense heart of Laniakea, where clusters crowd together and gravitational activity is intense, lies hundreds of millions of light-years from our solar system. This discovery also changed how astronomers define cosmic structures. Before Tully's work, supercluster boundaries were drawn based on where galaxies happen to cluster visually. After it, boundaries were defined by gravity, by where matter is being pulled together rather than where it happens to appear. That is a more meaningful line to draw, and when you draw it that way, the structure you find is considerably larger. Something in the data pointed further still. Even as the Laniakea boundaries were being confirmed, peculiar velocity measurements at larger scales were hinting at a pull from something much farther away. something 650 million light-years out, something 10 times larger than Laniakea itself. And in 2024, a new study made that hint harder to ignore. In October of 2024, the Cosmic Flows research team published new findings in Nature Astronomy. They had assembled the most precise and complete map of galaxy motions ever created, cataloging the movements of thousands of galaxies across hundreds of millions of light-years. And what they found was a signal they had not expected. There is a 60% probability, their analysis concluded, that the Milky Way is gravitationally bound to the Shapley concentration, a massive structure located 650 million light-years away. Harlow Shapley first noticed this region in the 1930s as an unusual concentration of distant galaxies in the direction of the constellation Centaurus. It looked denser than the surrounding universe, but without the tools to measure its full extent or mass, its true nature remained unclear for decades. When astronomers finally mapped it properly, what they found was immense. The Shapley concentration holds over 25 rich galaxy clusters. Its total volume is roughly 10 times greater than all of Laniakea. It represents the single most concentrated mass in our local universe, a gravitational presence so large that its influence extends hundreds of millions of light-years in every direction. What the 2024 study found was that the velocity flow of our galaxy and the surrounding region appears to point toward the Shapley concentration, suggesting a gravitational connection operating at a scale no one had previously assigned to our cosmic address. This is still recent science. The 60% probability reflects genuine, honest uncertainty. Further survey data, particularly from ongoing velocity mapping projects, will be needed to push that confidence higher or revise it downward. The science is alive and actively being tested. Tully described the broader picture. The discovery of these larger basins could fundamentally change our understanding of cosmic structure. There is a pattern running through everything we have covered so far. Every time astronomers zoom out one level, the structure above is larger than the models predicted. The local group leads to the Virgo cluster. The Virgo cluster sits inside Laniakea. And now, Laniakea may be flowing into the Shapley concentration. Each level reveals something bigger. Each answer opens a question one size larger. What makes this pattern unsettling is what it implies about our understanding of where we live. Humans have been charting the cosmos for centuries. We identified planets, mapped stars, discovered galaxies, and built increasingly sophisticated pictures of the universe's large-scale structure. And at each stage, the true scale turned out to be larger than we thought. Not by small margins, by factors of 10. By factors of 10 times 10. The cosmic address we thought was complete keeps having another flaw added above it, and yet all of it, from the Milky Way to the potential Shapley Basin, fits within the observable universe the way a single raindrop fits inside an ocean. Because the next level of structure in the universe is not measured in millions or even hundreds of millions of light-years. It is measured in billions, and it connects every cluster and supercluster into a single vast architecture spanning the entire observable sky. That architecture has a name, and between its threads lie regions of emptiness so extreme they raise questions that physics has not fully answered yet. The architecture connecting every cluster, every supercluster, every structure we have discussed has a name. Scientists call it the cosmic web, and when astronomers finally mapped it, what they saw did not look like a random scatter of galaxies across empty space. It looked like something alive. The cosmic web is a three-dimensional network of filaments, sheets, nodes, and voids, spanning the entire observable universe in every direction. It is real, confirmed by 4 decades of independent survey data, and it is the largest coherent structure in existence. The first clear map of it came in 1985, when astronomers Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics completed a survey of thousands of galaxies and plotted their positions in 3 dimensions. What appeared on the screen stopped people cold. Galaxies were arranged along sheets and threads, between them, enormous empty regions. The universe had texture, it had scaffolding. The cosmic web had been hiding in plain sight, waiting for a survey large enough to reveal it. Those filaments are immense. Individual strands stretch hundreds of millions of light years. They are built primarily of dark matter, invisible to every telescope, with visible galaxies clinging to their outer surfaces the way frost forms along a wire. The matter you can see is just the luminous edge of something far more massive underneath. Here is where something unexpected enters the picture. In 2020, a team of researchers discovered that these filaments spin. The largest filaments in the cosmic web rotate around their own long axes, like slow-motion cylinders of matter turning in the dark. They are now classified as the largest rotating objects ever identified in the observable universe. The mechanism driving this rotation is still being studied, but the observation itself is confirmed. In 2021, astronomers identified an ancient filament that formed just 830 million years after the Big Bang. It already contained 10 galaxies stretched across 3 million light-years. The web was assembling itself long before most models predicted. That changes what we thought we knew about how early the universe organized into structure. Where the filaments cross each other, gravity concentrates matter into the densest nodes in the observable universe. Every massive structure discussed so far, the Virgo cluster, the Great Attractor, the Shapley concentration, sits at one of these intersections. They are not isolated objects. They are knots in a web connected to each other by invisible threads spanning billions of light years. And then there is the other feature of the web, the one that dominates by volume. Between the filaments, vast regions contain almost nothing. No galaxies, no gas clouds, no stars. Just space, cold, dark, nearly empty space. These voids make up roughly 95% of the total volume of the observable universe. The universe is not mostly galaxies. The universe is mostly nothing. The galaxies and filaments are the minority, squeezed into a tiny fraction of the available volume like foam on the surface of an ocean. Computer simulations of the cosmic web at large scales produce images that routinely stop viewers in their tracks. The structure looks exactly like a human brain, a neural network, complex branching, clustering at nodes, long strands connecting distant concentrations. Scientists have noted this resemblance in peer-reviewed papers. It is a structural observation, not a metaphor. Networks shaped by similar constraints, whether gravity or electrochemical signaling, converge on similar patterns. But the most extreme expression of what the web produces is found in its empty spaces. And one of those spaces, discovered over 40 years ago, is large enough that traveling through it at the speed of light would take longer than complex animal life has existed on Earth. In 1981, a team of astronomers led by Robert Kirshner was conducting a systematic survey of galaxies in the constellation Boötes when they noticed something wrong. A large section of sky that should have contained roughly 2,000 galaxies contained almost none, 60. Out of 2,000 expected, 60 were found. In a region of space roughly 250 to 330 million light-years across, the density of matter inside was approximately 10% of the cosmic average, confirmed by follow-up surveys over the decades since. This is not a statistical fluke or an artifact of incomplete data. The Boötes void, as it became known, is real. It is enormous, and it is strange. Here is the comparison that makes the size concrete. The Milky Way is roughly 100,000 light-years across. The Boötes void could contain 3,000 Milky Way galaxies laid end-to-end across its width, with room to spare. Sitting about 700 million light-years from here, it represents one of the most dramatic underdensities anywhere in the observable universe. If you could travel through it at the speed of light, the journey would take over 250 million years. That number deserves to be held for a moment. 250 million years of flying at the maximum speed allowed by physics, through a region nearly devoid of any stars, any planets, any structure whatsoever. For almost the entire trip, you would see nothing. No bright galactic arms, no glowing clusters, just the faint glow of the cosmic microwave background and darkness ahead. 250 million years is roughly how long complex animal life has existed on Earth. The entire span from the first fish with legs to every civilization that has ever risen and fallen, all of that time compressed into a single crossing of one void. The 60-odd galaxies that do exist inside the Boötes void are unusual. Many have irregular shapes, high gas content, and continued star formation driven by internal processes rather than the environmental pressures galaxies in denser regions experience. Some appear arranged in a faint filamentary pattern, a miniature echo of the larger cosmic web forming within the emptiness itself, a web within a void. Gravity cannot help itself. Even in the most desolate regions of the observable universe, matter finds a way to reach for other matter. Now here is the part that should raise a specific kind of unease. The Boötes void is strange and enormous, but it is also comprehensible within standard cosmology. Gravity can clear a region that size over the age of the universe. The models allow for it, even if reluctantly. What cannot be so easily absorbed is the question of whether the Boötes void is an extreme outlier, or whether it is simply the most visible example of something far more common. The cosmic web fills the observable universe with voids of all sizes. Most are smaller, some are larger. And the largest confirmed example of all does not sit somewhere remote in the sky. It surrounds us completely. Standard cosmological models can accommodate the Boötes void. At 330 million light-years, it sits within the range of structures that gravity could have cleared over the universe's lifetime. The theory predicts voids of this size can form, though they remain extreme outliers. So the Boötes void is confirmed, well studied, and scientifically explicable, if deeply unsettling. What comes next is harder to explain, because there is a void far larger than the Boötes void, and we are inside it right now. Everything we have mapped so far sits within an underdense region of space roughly 2 billion light-years across. The Milky Way, the local group, Laniakea, the Shapley concentration, all of them sit inside a cosmic desert where the average density of matter is about 30% below the rest of the observable universe. This structure is called the KBC void, named for the researchers who formally described it in 2013, Keenan, Barger, and Cowie. At 2 billion light-years in diameter, it is one of the largest underdense regions identified anywhere in the observable universe. Let that settle. Every galaxy we have discussed, every supercluster we have named, everything from our immediate cosmic neighborhood out to several 100 million light-years in every direction. All of it is inside a bubble of space with less matter than the universe average. We live in a cosmic backwater. The scientific status here is honest. The KBC void is supported by observational evidence, but the depth of its underdensity remains contested. Some analyses suggest it is more pronounced than others indicate. This is an active research area, and the exact numbers are still being refined. What is not seriously disputed is that we do appear to live inside some degree of local underdensity relative to the broader universe. The details are in ongoing discussion. What makes this more than an abstract curiosity is what it might explain. For over a decade, cosmologists have been struggling with a problem called the Hubble tension. The rate at which the universe is expanding, when measured using nearby objects in our local region, consistently comes out about 9% higher than the same rate measured using the cosmic microwave background and the early universe. The two measurements should agree. They do not, and nobody has a fully satisfying explanation. One compelling possibility is exactly this. If we live in an underdense region, matter is less concentrated around us than in the average universe. Gravity is slightly weaker locally. The local expansion rate would be slightly higher than the global average because there is less gravitational resistance pulling things back together. Our local measurements would look inflated compared to the rest of the universe. The instruments would be working perfectly. The neighborhood simply expands a little differently. This remains a theory, worth taking seriously but not confirmed. The Hubble tension may have other explanations. Dark energy may be behaving in unexpected ways. There may be systematic errors in one or both measurement methods, or all of these factors may be contributing at once. What is certain is that we sit in an emptier than average region of the universe, and the ramifications of that are still being worked out. The universe, as we observe it, may be subtly biased by the specific underdense pocket we happen to occupy. This is a strange thing to absorb. Humans built their understanding of the cosmos from within this particular region of space. Every telescope pointed outward was pointed outward from inside this underdensity. Every expansion rate measured, every map of galaxy distribution drawn, every calibration of cosmological models, all of it was conducted from inside a pocket that differs from the average universe. We have been observing the universe from a slightly unusual seat. Whether that has distorted our picture, and by how much, is a question still being actively investigated by research teams around the world. And if emptiness defines one extreme of cosmic structure, the opposite extreme is something else entirely, because the cosmic web does not just produce voids. It also produces walls of galaxies so vast they challenge the mathematical limits of what should be possible. In 2016, the Sloan Digital Sky Survey had been running for over 15 years. It had mapped hundreds of millions of galaxies across enormous stretches of the sky, building the most detailed three-dimensional map of the observable universe ever created. Most cosmologists assumed that beyond a certain scale, roughly 1.2 billion light-years, the universe would look statistically smooth and uniform in all directions. This is called the cosmological principle, and it had never been seriously threatened. Then researchers Richard Gott III and Mario Jurich at Princeton University used the survey data to measure a structure already sitting in the maps, one that had been partially identified but never fully appreciated. When they calculated its length, the result came out to 1.37 billion light-years. The Sloan Great Wall, confirmed in October of 2003, it immediately became the largest known structure in the universe at the time. 1.37 billion light-years of galaxies, arranged in a sheet visible across an enormous arc of sky, located roughly 1 billion light-years from Earth. Its full length is approximately 1/60th of the entire diameter of the observable universe. It contains multiple galaxy superclusters arranged along its length like cities along a highway. The implications went beyond size alone. A structure that large poses a genuine challenge to the idea that the universe looks the same at all scales. The cosmological principle holds that if you zoom out far enough, the universe should appear uniform, with matter distributed evenly rather than clustered into specific patterns. The Sloan Great Wall was at the edge of what standard models could accommodate, right at the line where theory and observation began to make uncomfortable contact. To grasp why this matters, consider what the cosmological principle actually says. It says the universe, viewed at large enough scales, has no preferred location and no preferred direction. Matter is spread evenly. No region is special. The same statistics apply everywhere. This assumption underlies almost every cosmological calculation ever made, including the expansion rate of the universe, the age of the universe, and the predicted fate of the universe. If the assumption fails at large enough scales, a great deal of what we think we know becomes uncertain. Astronomers spent years debating whether the Sloan Great Wall was a true contiguous structure or just an alignment of separate features. Studies have continued to support its existence as a coherent large-scale feature. It remains in the catalogues of confirmed megastructures. One way to feel its scale. If you traveled along the Sloan Great Wall at the speed of light, the journey from one end to the other would take 1.37 billion years. That is longer than it took complex multicellular life to evolve from the first simple animals into everything currently living on Earth. The dinosaurs lived and vanished, every ocean filled with new species. Continents shifted, entire lineages of life arose and went extinct. And you would still be in transit. It held the record for the largest known structure for almost a decade. It was understood at the time to be extreme, an outlier, the kind of thing that pushes boundaries without breaking them. The cosmological principle, bending under its weight, was still technically intact. Then, a team of researchers in Hungary found something else. Something that made the Sloan Great Wall look like a minor detail in the map. In 2013, a team of astronomers led by István Horváth in Hungary made an unexpected discovery. They were studying the distribution of gamma-ray bursts, the most energetic explosions in the observable universe, across a large section of sky at a redshift of roughly 2. That places them about 10 billion light-years away. They found a statistically significant clustering of these bursts concentrated in a specific region of sky spanning the constellations Hercules and Corona Borealis. When they calculated the size of the region producing that overdensity, the number they arrived at was extraordinary. The structure stretched somewhere between 6.5 and 10 billion light-years across. It has since become known as the Hercules Corona Borealis Great Wall, and it remains the largest single structure ever identified in the observable universe. John Hakila, a professor of physics and astronomy who was part of the analysis, described the discovery simply. "We calculated it," he said, and then realized, this is the biggest thing in the universe. 10 billion light-years, 1/9 of the entire diameter of the observable universe. To cross it at the speed of light would require more time than the universe has currently existed, not slightly less. More, the universe is 13.8 billion years old. Crossing this structure end to end would take 10 billion years, from one side to the other, at the maximum speed physics allows. Put another way, the universe itself would have to be a third older than it currently is before you finished the crossing. And you would have been traveling since before the Earth formed. Here is why this is a problem. Standard cosmological models set a theoretical upper limit on how large a contiguous structure can be. Gravity has had 13.8 billion years to work with. In that time, the models calculate matter can only be pulled together and organized into structures roughly 1.2 billion light-years across at the very most. The Hercules Corona Borealis Great Wall is roughly 8 times larger than that limit. It should not exist. The structure is probably real. The statistical evidence is significant. Subsequent analyses with larger datasets continue to support it, but its scientific status remains at the level of highly probable, not definitively confirmed as a true single contiguous structure. The observational method, relying on gamma-ray burst distributions rather than direct galaxy mapping, carries specific uncertainties. Future missions may resolve the question. Until then, the possibility sits in the data like a warning light no one can explain. If confirmed as a genuine structure, the implications ripple outward into the foundations of cosmology. The standard model that describes how structure forms would be wrong in a meaningful way. The timeline of cosmic evolution would need revision. The processes that shaped the early universe within the first few billion years would have to have been more powerful or more organized than we currently understand. Something built this at a scale our best physics says should be impossible. There is one further thing to note. This structure sits 10 billion light-years away. Light from the region containing it has been traveling toward us for 10 billion years. And beyond roughly 18 billion light-years, something more permanent than distance begins to take hold. There is a boundary in space. It is not a wall you could see or an edge you could approach. It is a line defined purely by the mathematics of expansion, and it sits roughly 18 billion light-years from Earth in every direction. Beyond that line, space is expanding faster than the speed of light. Not because anything is moving through space at impossible speed, because the space itself between us and those distant regions is stretching so rapidly that light crossing it toward us loses ground. It can travel toward us for billions of years and still end up farther from us than when it started, carried away by the expanding fabric beneath it. This is the cosmic event horizon, and it is confirmed by the same physics that predicts black hole event horizons, simply operating at the scale of the entire observable universe instead of a single collapsed star. Every galaxy beyond 18 billion light-years is already gone, not destroyed, simply disconnected. Their light will never reach us, regardless of how long we wait. The signals they are sending right now will travel toward us forever and never arrive. Here is the number that makes this tangible. Every year, roughly 160 billion stars cross beyond that horizon, not in a single dramatic event, silently, steadily. 160 billion every year, slipping beyond any possible contact, forever removed from the observable universe. This is confirmed. The rate has been calculated, checked, and published. It is ongoing as you receive these words. The current observable universe contains roughly 2 trillion galaxies, but that is only about 6% of the total volume of space. The remaining 94% is already permanently beyond our event horizon. We cannot send signals there. We cannot receive signals from there. For every practical purpose, it no longer exists within the universe we can ever access. And this number is not fixed. The event horizon is not a stable boundary. As dark energy continues to accelerate the expansion of space, the horizon's effective reach in certain respects shifts over time. Regions we might theoretically communicate with today will eventually fall silent as the expansion rate increases. Think about the scale of what that means. The universe we can currently observe, that 93 billion light-year sphere containing 2 trillion galaxies, is already a small minority of what is out there. A minority being further reduced, year by year, at a rate of 160 billion stars per year. The universe we live in is shrinking, not the physical space, which is expanding. The part of the universe we can access, the part we can study, the part we can communicate with, even in principle, is getting smaller every year. There is something philosophically significant about this that rarely gets acknowledged. Every civilization that might exist in some distant galaxy right now, every possible form of intelligence that might be looking outward from its own world, faces this same diminishing horizon. Whoever they are, wherever they exist inside the observable universe, they are also losing their sky. Their event horizon is also pulling in. Their access to the broader universe is also being quietly revoked, the same as ours, 160 billion stars at a time. The universe is becoming a collection of isolated islands, slowly, over incomprehensible timescales, but steadily, and the future trajectory of this process leads somewhere far more isolating than anything we have discussed so far. Because if you wait long enough, and here long enough means trillions of years rather than billions, what is left will be almost unimaginable in its loneliness. Imagine a civilization 2 trillion years from now. Not 2 billion, 2 trillion. That is roughly 145 times the current age of the universe. Any planet capable of hosting such a civilization would need a stable stellar host, a very slow-burning red dwarf, and the patience of deep time. What would that civilization be able to observe? Almost nothing of what we can see today. Confirmed physics tells us what happens as dark energy continues accelerating expansion. Galaxy clusters outside our local group are currently still visible, but they are receding. Over trillions of years, each one crosses beyond the cosmic event horizon. One by one, galaxy after galaxy fades below detectability, redshifted into silence, pushed past the boundary where its light can ever reach us. In roughly 2 trillion years, based on current expansion models, every galaxy outside our own local group will have crossed that boundary permanently. The Virgo cluster, Laniakea, the Shapley concentration, all of those structures we mapped with such care will be cosmically gone, not destroyed, just unreachable, invisible, silent. The night sky of that future civilization will contain one galaxy, the merged remnant of the Milky Way and Andromeda, which will have completed their collision in about 4.5 billion years, forming a single massive elliptical structure. That structure, that one object, will be the entire observable universe for anyone living in it 2 trillion years from now. Here is the deeper problem. That future civilization will have no way of knowing what they are missing. They will see a single galaxy surrounded by empty darkness. They will have no observable evidence that the universe once contained 2 trillion more. The cosmic microwave background, the ancient glow of the Big Bang that fills our sky in every direction and tells us how the universe began, will have been stretched by expansion until it falls below any possible measurement threshold. The temperature will drop to a fraction of a degree above absolute zero. No instrument will detect it. They will conclude, reasonably and incorrectly, that the universe is a single static galaxy in an infinite, eternal void. No Big Bang, no expansion, no cosmic history. Now, consider what that means about the nature of scientific knowledge itself. All of cosmology, the entire enterprise of understanding the origin, structure, and fate of the universe, depends on the ability to observe evidence that currently exists. If you had been born in that far future era, the evidence would simply not be there. No amount of intelligence or technology would help. The information would be gone, permanently removed by the quiet violence of expansion. The future is not just lonely, it is epistemically sealed. It will be impossible to know the truth. Lawrence Krauss summarized this precisely. "We live at a very special time," he said. "The only time when we can observationally verify that we live at a very special time. This cuts through everything. The evidence for the universe's history is available right now, in this era. And that availability is temporary, which raises the question of exactly when we are in cosmic time, and what it means that we happen to be here to ask it. Consider the full timeline. The universe is 13.8 billion years old. The first stars formed about 200 million years in. The first galaxies assembled within the first billion years. Our solar system formed roughly 9 billion years after the Big Bang. Life appeared on Earth about 4 billion years ago. Complex animals arose around 500 million years ago. Modern humans have existed for about 300,000 years. This particular moment in cosmic time, the era we occupy right now, has a specific and unusual character. It sits in what cosmologists increasingly describe as a golden age of observation, a narrow window in cosmic history when all the evidence needed to understand the universe is still present and accessible. The cosmic microwave background is still detectable. It still fills the sky with the faint thermal signature of the Big Bang. It can still be measured, mapped, and used to confirm the age, composition, and geometry of the universe. In a few trillion years, that signal will be gone. Distant galaxies are still visible. We can still observe structures billions of light years away, see the early universe as it was hundreds of millions of years after the Big Bang, and confirm the history of cosmic evolution. In a few trillion years, those galaxies will be beyond the event horizon. The expansion of the universe is still visible in the recession of distant objects. We can still measure the rate of expansion, identify dark energy's influence, and map the large-scale structure of the cosmos. In a far future era, that evidence will also be inaccessible. Everything that allowed cosmology to exist as a science, all of the observable evidence for how the universe works, is accessible within a specific window, and we happen to be in it. Think about how unusual that is. The universe is old enough that stars and planets and biology have had time to develop. Intelligence exists. Technology exists. Telescopes exist. And the evidence of the universe's own history is still radiating toward us from every direction. These three things, old enough for complex life, young enough for evidence to survive, technologically capable of reading that evidence, overlap in a window that does not last forever. The window is estimated at roughly the first 100 billion years after the Big Bang. We are 13.8 billion years in. Early in the window, the evidence is all still present. Every observation astronomers make right now would be impossible for any civilization coming after this era of cosmic time. Future generations, if they exist far enough forward in time, will inherit a universe stripped of its history. All the observations we are making, every image from every telescope, every measurement of every distant galaxy, may represent the only record that will ever exist of what this universe actually contains. That is an unusual weight to carry, and it brings a very specific question into focus, because so far, We have only been discussing the part of the universe we can see. Everything we have covered, every galaxy, every void, every filament, every supercluster, represents only 5% of what is actually here. Everything discussed up to this point, every galaxy, every star, every planet, every atom of ordinary matter in the observable universe, all of it combined, accounts for just 4.9% of what exists. Stop there, 4.9%. The remaining 95.1% is invisible to every telescope ever built. It emits no light, reflects no light, and absorbs no light. It cannot be photographed. It cannot be directly detected by any instrument currently in existence. And yet, it is there. Confirmed by multiple independent lines of evidence so strong that its existence is no longer seriously questioned. What is questioned, and still completely unknown, is what it actually is. Keith Bechtold, a physicist at the University of Wisconsin-Madison, stated the situation plainly. This, he said, is a stringent test of the current standard cosmological model, a model proposing that 95% of the universe is dark matter and dark energy that we do not yet understand. The breakdown, confirmed by the Planck satellite's measurements of the cosmic microwave background published in 2018, is precise. 4.9% is ordinary matter. That is everything you have ever seen, touched, or measured. Every star, every nebula, every black hole with an accretion disk bright enough to photograph, every element on the periodic table, every molecule in every organism that has ever existed, all atoms, all chemistry, all matter that has ever interacted with light, 4.9% of the total. 26.8% is dark matter, an invisible substance distributed throughout every galaxy and galaxy cluster, providing the gravitational scaffolding that holds the visible universe in place. The Milky Way exists inside a dark matter halo. Every structure in the cosmic web was assembled along dark matter filaments. The entire visible universe is a thin, luminous layer draped over something we cannot see. 68.3% is dark energy, a force causing the expansion of space to accelerate, with a theoretical origin so poorly understood that the leading prediction from physics is off by a factor of 10 to the power of 120. That is not a typo. The theoretical prediction and the observed value disagree by 120 orders of magnitude. It is the largest discrepancy between theory and measurement in the entire history of science. Together, dark matter and dark energy compose the overwhelming majority of reality. And we have essentially no idea what either of them is at the fundamental level. Consider what that means for everything discussed so far. Every filament of the cosmic web is a dark matter filament that galaxies happen to trace. Every galaxy cluster is held together by dark matter. Every rotation curve of every spiral galaxy reflects the pull of dark matter halos extending far beyond the visible disk. The visible universe is, in a real sense, just the light show produced by a structure we cannot see or touch. The real universe, by volume and by mass, is overwhelmingly dark. The universe we have been exploring in such detail is built on a foundation we cannot see, and that foundation has been revealing itself slowly, across nearly a century, through the motions of objects and the bending of light, in places we least expected to find something invisible. Fritz Zwicky was not looking for invisible matter. In 1933, he was trying to understand the Coma cluster, a dense concentration of roughly 1,000 galaxies sitting about 320 million light-years from Earth. He measured the velocities of the galaxies inside it. Then he calculated how fast they should be moving, based on the total visible mass present. The numbers were wrong by a factor of several hundred. The galaxies were moving so fast that the visible mass of the cluster could not provide enough gravity to hold them together. If only ordinary matter existed in the Coma cluster, the galaxies should have been flying apart long ago. Something else was there, something with enormous gravitational mass that produced no detectable light. Zwicky called it Dunkel Materia, dark matter, and published his conclusion in 1933. The scientific community largely ignored him for 30 years. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford took a different approach. They measured how fast stars orbit within the outer edges of spiral galaxies. By the laws of gravity, stars far from the galactic center should orbit more slowly than stars closer in, for the same reason the outer planets of our solar system move more slowly than the inner ones. Rubin and Ford measured galaxy after galaxy and found the same unexpected result everywhere. Stars at the outer edges were orbiting just as fast as stars near the center, sometimes faster. The only explanation that fits is invisible mass, extending far beyond the visible edges of every galaxy they studied. An enormous dark halo surrounding each one, providing extra gravitational pull across the entire structure. In 2006, a pair of colliding galaxy clusters called the Bullet Cluster provided some of the most direct evidence yet. When two clusters collide, the hot gas in each cluster is slowed down by the collision and lags behind. If most of the mass were in that gas, the gravitational center of each cluster would shift toward the gas. Instead, measurements showed the gravitational centers of both clusters had passed straight through the collision zone without slowing, clearly separated from the gas. The gravitational mass was not in the gas. It was in something that barely interacted with anything at all, except through gravity. Dark matter had moved through the collision as if the ordinary matter simply was not there. As of 2026, not one particle of dark matter has ever been directly detected in a laboratory. The experiments searching for it are extraordinary. Detectors buried deep underground, shielded from every possible source of interference, cooled to near absolute zero, waiting for a single dark matter particle to nudge an ordinary atom. Years of waiting, trillions of particle interactions recorded, and nothing, zero confirmed dark matter signals. Its identity remains completely unknown. The candidates range from heavy particles called weakly interacting massive particles to ultralight particles called axions, to primordial black holes formed in the early universe. Every candidate remains unconfirmed. Dark matter is the majority of all matter in the universe. It built the cosmic web. It holds every galaxy together. Every structure we have explored exists because of it, and we cannot say what it is. But dark matter is only 27% of the universe. The dominant force, the one tearing the cosmos apart at an accelerating rate, is something far stranger. In 1998, two independent teams of astronomers were doing something unglamorous. They were measuring the brightness of exploding stars, specifically a type of explosion called a Type Ia supernova, which always produces a reliably consistent peak brightness. That makes it a useful distance marker. If you know how bright something truly is, and you measure how dim it appears from here, you can calculate exactly how far away it is. Both teams were using this technique to map the expansion rate of the universe with precision. They expected to confirm that the expansion was slowing down. Gravity has been pulling matter together since the Big Bang, and the assumption was that this pull would be gently putting the brakes on everything. The plan was simple: measure the deceleration, confirm the models, move on. Instead, they found the opposite. The supernovae were dimmer than expected, farther away than they should have been. The universe was speeding up. The expansion of space was accelerating, and had been doing so for roughly 5 billion years. Something was pushing outward across the largest scales of the cosmos, overcoming gravity everywhere, driving everything apart at an ever-increasing rate. They named it dark energy. Adam Rees, Saul Perlmutter, and Brian Schmidt shared the Nobel Prize in Physics in 2011 for this discovery. The acceleration is confirmed. The discovery is not in doubt. What causes dark energy remains completely unknown. What we do know is this: dark energy behaves like a property of empty space itself. Even a perfect vacuum, stripped of every particle, carries a baseline energy. Einstein originally included a term in his equations representing exactly this kind of energy, which he later abandoned when expansion was discovered. The discovery of dark energy brought something very like that term back into the equations, vindicated in the most unexpected way. The problem is the numbers. Quantum field theory, the most precisely tested framework in all of physics, predicts what the energy density of empty space should be. When you calculate it from first principles, the answer comes out roughly 10 to the power of 120 times larger than what we actually observe. 120 orders of magnitude off. It is the largest known discrepancy between a theoretical prediction and a measured result in the entire history of science. No one has a satisfying explanation for why the actual value is so small. What dark energy does is clear enough at cosmic scales. It stretches the fabric of space faster than gravity can pull it back together. At the scale of galaxies and clusters, gravity still wins. The Milky Way is in no danger of being pulled apart. But at scales larger than superclusters, the tension has already been decided. Dark energy is winning. Every year, more of the universe accelerates beyond our reach. In 2024, new results from an instrument called the Dark Energy Spectroscopic Instrument hinted that dark energy may be evolving over time. The significance of those results is currently rated at about 3 sigma, which is suggestive but not yet definitive. Confirmed or not, the implication is unsettling. If dark energy is changing, our entire framework for the universe's future may need revision. The acceleration is real, the cause is a mystery, and somewhere inside this expanding, accelerating universe sits the oldest light in existence, arriving from every direction at once, carrying a message from before any galaxy ever formed. Something is reaching you from every direction at this exact moment. You cannot see it, you cannot feel it. But it is there, measurable by any sensitive enough detector, permeating every cubic inch of space in the observable universe in all directions simultaneously. A faint, cold bath of microwave radiation. The cosmic microwave background, the oldest light in existence, and it is confirmed, measured in extraordinary detail by multiple independent missions spanning 40 years. To understand what it is, you need to go back to when the universe was very young. For the first 380,000 years after the Big Bang, the universe was too hot for atoms to exist. The temperature was so extreme that every time a proton and an electron came close enough to bind together, surrounding photons immediately blasted them apart again. The universe was an opaque, glowing plasma. Light could not travel more than a short distance before hitting something and scattering. If you could somehow stand outside it and look in, the universe would have resembled the interior of a star, dense, blindingly bright, impenetrable. Then the universe expanded enough to cool down. Somewhere around 3,000 degrees, electrons finally lost enough energy to stay bound to protons. Hydrogen atoms formed. This moment is called recombination, and it is confirmed by multiple lines of evidence. When it happened, there was suddenly nothing left to scatter the light. Photons that had been trapped for 380,000 years had a clear path for the first time. They streamed outward in every direction at once. We detect those photons today. Their temperature has cooled from 3,000 degrees at emission to just 2.726 Kelvin now, which is 454.8 degrees below 0 Fahrenheit, barely above absolute zero. The expansion of the universe has stretched their wavelengths enormously, shifting them from infrared light down into the microwave range, far below what human eyes can detect. 12% of the static in old analog television sets came directly from this signal, photons that had been traveling for 13.8 billion years arriving at the antenna, the faint hiss of creation, audible on a broken television set. The uniformity of this signal is extraordinary. The temperature barely varies from one patch of sky to another. The fluctuations are only about 1 part in 100,000. But those tiny variations matter enormously. They represent the slight density differences in the early universe that gravity later amplified over billions of years into every galaxy, every filament, every void we have discussed. The entire structure of the observable universe was already written in these fluctuations, long before a single star had formed. The surface from which this light was emitted sits 46.5 billion light-years away in every direction. That is the furthest back in time we can see using light. Before that, the universe was opaque. Our view stops at 380,000 years after the Big Bang. Beyond that edge of the visible past, the early universe waited, and the universe as a whole, confirmed to extend far beyond what we can see, is very much larger than this sphere of ancient light. How much larger is a number that changes the scale of everything discussed so far? The observable universe is large. It is almost certainly a tiny fraction of the total universe. The evidence comes from geometry. Measurements of the cosmic microwave background by the Planck satellite, published in 2018 and confirmed by multiple independent analyses, show that the universe is geometrically flat. The angles of triangles drawn across enormous stretches of space add up to exactly 180 degrees, confirmed to within 0.4%. This is a fact about the structure of the universe, and it has consequences. A flat geometry is mathematically consistent with one specific outcome: an infinite universe, a universe with no edges, no center, extending in all directions without limit. Infinity is not confirmed as absolute fact. What is confirmed is the flatness to the precision of current measurements. Every data point collected supports it. From this starting point, researchers have calculated how much larger the total universe must be compared to the observable portion. In 2011, researchers Mihran Vardanyan, Roberto Trotta, and Joseph Silk at Oxford University applied Bayesian statistical analysis to the available data and arrived at a lower bound. Their result: the total universe is at least 250 times larger than the observable universe in volume. That is the minimum, the floor, the smallest it could be while remaining consistent with what we observe. Inflation pushes this number into a different category entirely. If space underwent the rapid exponential expansion most cosmologists believe occurred in the first tiny fraction of a second after the Big Bang, then the total universe would be at least 3 times 10 to the 23rd power times larger than what we observe. That is the number 3 followed by 23 zeros, applied as a multiplier to the 93 billion light-year sphere explored throughout this journey. At the extreme end, certain theoretical calculations suggest the total universe may be 10 to the power of 10 to the power of 122 times larger. Writing this number would require more space than the observable universe contains. It is meaningful only as a mathematical object. Even the conservative estimate, 250 times larger, reshapes everything. The observable universe holds 2 trillion galaxies. At 250 times the volume, the total universe holds at minimum 500 trillion galaxies, 500,000 billion galaxies, all operating under the same physical laws, the same stars, the same chemistry. Every structure explored in this journey, every filament and void and wall, repeated across a canvas 250 times larger at minimum, probably far, far more. Here is the thing that makes this personal rather than merely abstract. If the total universe is even 250 times larger than what we see, then the entire volume we have mapped, every galaxy ever imaged, every supercluster ever named, every void ever crossed at the speed of thought, represents less than 0.5% of what physically exists. Our most complete portrait of the cosmos is a postage stamp on a canvas we cannot see the edges of. And if the universe is genuinely flat and infinite, the repetitions do not simply stop somewhere, they continue without any limit at all, which produces a specific, deeply strange consequence that mathematics refuses to let go of. If the universe is infinite, you have a copy. Follow the logic. The observable universe contains a finite amount of matter. Quantum mechanics sets a finite number of distinct states that any finite region of space can occupy. That number is incomprehensibly large, but it is finite, a finite set of possible arrangements of particles and energy within a region the size of our observable universe. In an infinite universe, a finite set of possible configurations must eventually repeat. Every arrangement of matter that can occur must occur, somewhere, an infinite number of times. This is not speculation. It is a mathematical property of infinity itself, as certain as the rules of arithmetic. The physicist Max Tegmark at the Massachusetts Institute of Technology calculated roughly how far away the nearest region of space configured identically to our observable universe would be. His estimate comes out at approximately 10 to the power of 10 to the power of 115 meters. This number is so vast that there are no useful comparisons to offer. The observable universe itself spans fewer than 10 to the 27 meters. The distance to your nearest identical region makes the observable universe look like a single step on a journey crossing the entire Earth, but the distance does not change the conclusion. If the universe is infinite, that region exists. Inside it, a planet configured identically to Earth. A copy of every continent, every city, every room. A copy of you, assembled from the same atomic configuration, carrying the same memories up to this exact moment. That copy is genuinely a different person in the sense that experience is continuous and theirs is separate from yours. But the configuration is identical. The decisions being made there are the same decisions. The thoughts arriving there are the same thoughts. The words being received there are these exact words. This is the most conservative type of multiverse. Researchers call it Level 1, and it requires nothing exotic, no extra dimensions, no alternative physics. Only two things: an infinite universe and the same physical laws operating throughout it. Both conditions are consistent with all current measurements. Neither has been contradicted by any observation. In an infinite universe, every possible variation of every possible person exists somewhere, not because the universe made them intentionally, because the space of possible configurations is finite and the universe is infinite, and therefore all of those configurations occur. Every outcome that did not happen here happened somewhere. Every path not taken here was taken there. Some cosmologists find this conclusion an elegant and inevitable consequence of well-tested physics. Others find it philosophically unsatisfying precisely because it can never be tested. Those copies exist beyond any horizon. They cannot send signals, they cannot be reached. The separation is permanent and absolute, and there is a deeper discomfort here. If identical copies of you exist and make identical decisions, what does that say about the sense of being a unique person in a unique moment? The physics does not answer that. It only confirms the geometry and lets the question sit there. The Level 1 multiverse requires only that the universe keeps going past the observable horizon. And so far, nothing in the data suggests it stops. But what comes next asks a far stranger question. It asks whether there might be entire universes where the laws themselves are completely different. In 1981, a physicist named Alan Guth at the Massachusetts Institute of Technology proposed that in the first tiny fraction of a second after the Big Bang, space expanded exponentially, doubling in size over and over in intervals so short they have no comparison in human experience. This process, called cosmic inflation, was proposed to explain several otherwise baffling features of the universe. Why does the cosmic microwave background look the same in all directions, even in regions that had no time to communicate? Why is the geometry so flat? Inflation answered both with elegance. The observational predictions it makes match the data with remarkable precision. The evidence for some version of inflation is strong, confirmed at the level where taking it seriously is entirely reasonable. But inflation carries a consequence that even Guth did not fully anticipate. Stopping inflation uniformly everywhere simultaneously requires a very specific set of conditions. Andre Linde showed that in most regions of space, the inflationary field stays in a high energy state and inflation continues forever. In small bubbles, quantum fluctuations cause the field to drop, inflation stops locally, and what forms inside each bubble is a universe. Our universe is one such bubble. In the larger inflating space surrounding it, other bubbles are constantly forming. Each one is a separate universe. String theory suggests roughly 10 to the power of 500 possible stable energy states the field can settle into. Each state would produce different physical constants, different particle masses, different strengths of the fundamental forces, different chemistry. Many of those states would produce universes where stars cannot form, where atoms are unstable, where complexity is impossible. Some might produce stranger configurations we cannot imagine from inside our own set of physical laws. Consider what different constants would actually mean. If gravity were even slightly stronger, stars would burn out within millions of years rather than billions, leaving no time for planets to form or life to develop. If the strong nuclear force were weaker, protons would not hold together, atoms would not exist. If dark energy were even a little larger, the universe would have expanded so rapidly after the Big Bang that matter could never have clumped together into anything at all. We exist in a remarkably narrow window of physical constants. Bubble universes with different values would mostly be empty, dark, and structureless. This is called the Level 2 multiverse, an enormous collection of bubble universes, each potentially operating under different physics, expanding away from each other inside an eternal inflating space they can never cross to reach each other. Here is the honest scientific status. Eternal inflation emerges from a framework with strong observational support. The bubble universes themselves are beyond any observable horizon and by definition cannot send signals to us. There is no direct evidence for any of them. Searches for possible signatures of a collision between our bubble and a neighboring one, which would leave a mark in the cosmic microwave background, have returned only negative or ambiguous results. Paul Steinhardt, one of the physicists who helped develop inflation in the early 1980s, has become one of its sharpest critics because of exactly this. If inflation produces a multiverse where every possible outcome occurs somewhere, he argues, then the theory makes no specific predictions. Any observation becomes consistent with it. A theory that can accommodate every result confirms nothing. That criticism has real weight. The mathematics of eternal inflation are real, but the implications have reached a place where physics and philosophy begin to blur, and that raises a challenge at the deepest level of how science works. Science is built on one core requirement. A good theory must make predictions that observations could prove wrong. Without that, a theory is not science. It is philosophy at best, unfalsifiable belief at worst. This standard was articulated most clearly by the philosopher Karl Popper, and most working scientists accept it as the minimum threshold a theory must meet to qualify as genuine knowledge. The multiverse, in most of its forms, fails this test. If there are infinitely many universes with every possible set of physical laws, no observation you can make in this universe could be inconsistent with that theory. Every possible outcome is accommodated somewhere. The theory cannot be disproved, and a theory that cannot be disproved cannot be confirmed either. It simply encompasses everything and explains nothing. This is a criticism coming from inside the physics community, from researchers who spent careers developing the very theories leading to the multiverse. Steinhardt stated it plainly. In a multiverse, any outcome is equally possible, so inflation makes no predictions. Leonard Susskind at Stanford University, who championed the string theory landscape and its connection to the multiverse, publicly stated in 2024 that he is 100% certain that string theory as a complete theory of everything does not describe reality. He was not dismissing all of its mathematics, but the concession carries weight from one of the idea's most prominent advocates. In 2014, researchers Ikjot Singh Kohli and Michael Haslam published an analysis suggesting that eternal inflation may not actually be eternal. Their modeling of the inflating field showed that solutions diverge in finite time. If inflation ends everywhere, the bubble-forming process stops. Many cosmologists dispute their analysis. The debate is ongoing. There is something important to recognize about this moment in science. The crisis is real, but it is not a sign of failure. It is a sign of progress, reaching a new kind of boundary. Every previous era of physics eventually hit a wall that required new tools, new mathematics, and new ways of thinking to pass through. Classical mechanics worked until it met the atom, and quantum mechanics was built to go further. General relativity described gravity beautifully until it ran into singularities and the beginning of the universe. And inflation was developed to reach past those limits. The current boundary is different in character. Previous walls were empirical. You could build new instruments and measure your way through. The multiverse boundary may be epistemological. The information needed to test it may simply not exist within any observable region. That is a new kind of challenge, and science does not yet have a consensus answer for how to handle it. Consider what this moment represents in the broader story. Humanity mapped the observable universe across 93 billion light-years. We identified the composition of reality back to the first fraction of a second. We extrapolated the fate of the cosmos across trillions of years. All of this from a single planet around an ordinary star in one galaxy out of 2 trillion, and we have arrived at an edge. The edge of what science can currently resolve. Beyond the observable universe, physics either continues as it does here, or it varies bubble by bubble across an eternal inflating sea, or the question lies permanently outside the reach of any observation. We do not know which. The evidence that would distinguish between these possibilities may not yet exist, or it may never exist. What is not in doubt is the scale of the confirmed universe itself. And within that confirmed universe, one photograph taken on a specific day says something about our location inside it that no number can quite match. Valentine's Day, February 14, 1990. Voyager 1 had been traveling away from Earth for over 12 years. Engineers calculated that before the probe flew beyond the range where a camera command could successfully execute, there was a brief window to turn its instruments back toward home. The idea came from Carl Sagan, who had argued for this photograph for years against the objections of team members who pointed out its negligible scientific value. Sagan insisted. The command was sent. The resulting image shows a scattered ray of light crossing the frame. In that ray, faint, barely a pixel wide, a pale blue point. Earth. Voyager was 3.7 billion miles from Earth when it took that photograph. By any human standard, that is an incomprehensible distance. By cosmic standards, it is essentially the front step of the house. The nearest other star is 25 trillion miles away, roughly 7,000 times farther than Voyager was. The center of the Milky Way is about 260 million trillion miles away. The nearest large galaxy is 25 million trillion miles away. The edge of the observable universe is approximately 70 trillion times farther than Voyager's position. The Voyager probe, launched in 1977, is still the most distant human-made object in existence. Almost 50 years of continuous travel at roughly 38,000 miles per hour, and it has barely left the front yard. At its current speed, it would need roughly 73,000 years to reach the nearest star. The observable universe edge, at that speed, would require a journey of about 1.7 billion years. We built the fastest object in human history, and it cannot meaningfully close the distance to even our closest neighbor. Every war ever fought, every empire that rose and fell, every ocean crossed, every face loved, every moment of suffering and joy across hundreds of thousands of years of human existence. All of it happened on that pixel. Carl Sagan wrote about it with exact language. That dot, he said, is here. It is home. It is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of joy and suffering. Thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every hopeful child lived there, on a mote of dust suspended in a beam of light. He was not being poetic, he was being precise. The photograph is a data point. The data says that everything humans have ever considered important occurred on an object invisible in almost every cosmic image ever taken, because it is too small and too faint to register. Our posturings, he continued, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. 3.7 billion miles, our front step, the maximum distance from which anyone has ever photographed Earth, and from there it barely shows. Somewhere far beyond that pale point, the entire span of human existence compresses into a sliver of time so thin it almost disappears against the full scale of cosmic history. The scale of space is one kind of vertigo. The scale of time produces something different entirely. And what you find when you place everything humans have ever done against the timeline of the universe may be the hardest thing in this entire journey to hold. Press the full history of the universe into one calendar year. Let January 1st at midnight be the Big Bang, 13.8 billion years ago. Let December 31st at midnight represent right now. Every single day on this calendar represents about 37.8 million years of real time. The Big Bang fires at the first moment of January 1st. For the first several weeks of this calendar, the universe contains only hydrogen, helium, and trace lithium. No stars, no light points in the dark. The first stars ignite around January 22nd. They are massive, short-lived, and their deaths seed space with heavier elements for the first time. Slowly, across weeks of calendar time, galaxies begin to pull together. The Milky Way forms around March 16th, still young, still growing. The cosmic web is taking shape in every direction. By early September, a cloud of gas and dust in one arm of the Milky Way begins to collapse. September 2nd, a new star at the center of that cloud ignites. September 21st, a small rocky planet solidifies in orbit around it. That planet is Earth. The first life appears October 3rd, single-celled, fragile, working out the chemistry of existence. It takes until November 21st for photosynthesis to develop, until December 5th for the first complex, multicellular animals to appear in the oceans. December 13th, fish with backbones. December 20th, the first forests. December 25th, one of the great extinction events, killing the majority of species alive at the time. December 28th, the first dinosaurs appear. They persist across several full days of this calendar. They are extraordinary in their variety and dominance. Then, on December 30th, the asteroid arrives. December 31st. In the hours before midnight, small mammals diversify into forms we recognize. Deep in the evening, the primate lineage branches away from the ancestors of everything else. By late evening, the ancestors of modern humans appear. And then, in the final 10 seconds before midnight, everything that human beings have ever done occurs. 10 seconds. All of it. Agriculture, the first cities. Ancient Egypt, spanning 3,000 years of civilization. Greece, Rome, the Dark Ages, the Renaissance, the Scientific Revolution, the Industrial Revolution. Every war, every discovery, every face ever known, every empire ever built or destroyed. The Wright brothers, nuclear weapons, the moon landing, the internet, this exact moment. 10 seconds on a calendar representing 13.8 billion years. The dinosaurs had December 28th to December 30th, 2 full calendar days, 160 million years of actual existence. They were here 240,000 times longer than our civilization has been. And they are gone. Modern humans, meaning our species with roughly our brain architecture, have existed for about 300,000 years. On this calendar, that is less than 0.8 of a second. Our oldest artifacts go back perhaps 40,000 years, half a second. The invention of writing, the thing that separates recorded history from prehistory, happened about 5,000 years ago, less than 1/10 of a second. Everything you have ever been taught about human history, every great figure, every civilization, every conflict, every breakthrough in science or art or politics occurred within that 10th of a second, sitting at the end of December 31st. After over 8 months of the universe existing before Earth even formed. This picture, held alongside the distances and the voids and the structures, produces something between two feelings. One is a weight that is difficult to name. The other requires looking in a different direction entirely, back to where the atoms in your body came from, long before Earth existed. Start with the iron in your blood. That iron was forged inside a dying star. This is a confirmed physical process. Iron cannot be produced in the Big Bang. The Big Bang made hydrogen, helium, and trace lithium. Everything heavier required the interior of a star with sufficient temperature and pressure to fuse lighter nuclei into heavier ones. Carbon forged in helium fusion. Oxygen built from carbon, silicon, sulfur, and ultimately iron, assembled layer by layer in the core of a massive star as it burned through successively heavier fuel. When that star finally built up enough iron in its core, it could no longer generate energy from fusion. Iron fusion absorbs energy rather than releasing it. The core collapsed. In a fraction of a second, it contracted from an object hundreds of miles across to something roughly 10 miles wide, then bounced back outward in an explosion so violent it briefly outshone the combined light output of every star in the galaxy, a supernova. The heavier elements forged in that explosion, including many of the trace elements in your body, were scattered through the surrounding space. Billions of years later, some of those atoms drifted in a gas cloud in the Milky Way. Gravity pulled the cloud inward. A new stellar system condensed from the material. The leftover mass, including that iron from the dead star, settled into orbiting rocks that eventually cooled and merged into a planet. You are made of that planet. And that planet was made of that dead star. And that dead star was made of earlier stellar explosions, stretching back across generations of cosmic recycling to the hydrogen that came from the Big Bang itself. The calcium in your bones was forged in stellar cores. The oxygen you are breathing was produced by stellar fusion and dispersed by supernovae. The carbon forming the backbone of every biological molecule in your body is stellar ash. The iron carrying oxygen through your bloodstream was forged in a star that exploded billions of years before Earth existed. Neil deGrasse Tyson has called this the most astounding fact he knows. The atoms that comprise life on Earth, he explained, are traceable to the centers of high-mass stars that exploded their enriched material into the galaxy, enriching gas clouds with the chemistry of life. Here is what that means. The universe did not simply produce a backdrop against which life happens to exist. The universe assembled the matter that became life through an unbroken chain of physical processes spanning billions of years and countless generations of stellar death and rebirth. The boundary between you and the universe is less clear than it appears. You are the universe, organized into a configuration capable of looking back at itself. Every cosmological process in this journey connects in a direct physical chain to this exact moment. The Big Bang produced the hydrogen. Stellar fusion built the heavier elements. Supernovae scattered them. Planetary formation concentrated them. Chemistry arranged them into complexity. And here you are, assembled from cosmic debris, aware of where you came from. The scale that seems to diminish us is the same scale that built us, and what that means for everything else deserves one final look at the whole picture. Take everything. 93 billion light-years across, 2 trillion galaxies, at least 10 to the power of 24 individual stars. A cosmic web of dark matter filaments stretching in every direction, built across 13.8 billion years from the faintest quantum fluctuation in the first fraction of a second. Voids, so empty that crossing them at the speed of light takes longer than complex animal life has existed on Earth. Structures so large that a journey from one end to the other would outlast the current age of the universe. Add the invisible portion. dark matter holding every galaxy together, confirmed by every observational method except direct detection, its identity completely unknown after nearly a century of searching. Dark energy driving the expansion of space at an accelerating rate, with a theoretical prediction so far off that the discrepancy is the largest known failure in the history of quantitative science. Together, 95% of reality, invisible, undetectable, dominant. Add the future. 2 trillion years from now, every galaxy outside our local group will have crossed the cosmic event horizon permanently. The cosmic microwave background will have faded below any possible measurement threshold. Future inhabitants will look outward and conclude, accurately by every measurement available to them, that they live in a single eternal galaxy in an empty void. They will have no way of knowing what was lost. The information will simply be gone. Now consider the confirmed lower bound. The total universe is at least 250 times larger than what we have just explored. Every galaxy, every void, every filament, every structure we named, repeated across a canvas, 250 times more vast, at minimum. Inflation models push that multiplier toward numbers that cannot be written in any available space. And then place yourself inside all of this. On a planet that forms 1 pixel in a photograph taken from our cosmic front step. In a civilization occupying 10 seconds on a calendar of 13.8 billion years, made from atoms forged in stellar explosions that predate Earth. Living inside the narrow golden window of cosmic history when the evidence of everything that happened before is still present in the sky, still detectable, still readable. Christopher Consolis, who established the 2 trillion galaxy count, noted that 90% of those galaxies have never been studied. The golden age of discovery is happening right now, in this era, with the instruments we have built, in the window that will not stay open forever. Lawrence Krauss was precise. We live at a very special time. The only time when we can observationally verify that we live at a very special time. There is a feeling that arrives when you hold all of this at once. The universe is enormous beyond any comfortable scale, mostly invisible, mostly empty, and entirely indifferent to whether any part of it is ever understood. It will keep expanding regardless of whether anything looks at it. The voids will keep deepening. Dark energy will keep its patient, relentless work, and yet, in this particular region, on this particular planet, in this particular 10-second moment, a small fraction of the universe organized itself into forms that ask questions about all the rest of it. That is not required by any physical law anywhere. It is not predicted by any equation. It simply happened. The same universe that assembled the Hercules Corona Borealis Great Wall assembled the awareness capable of measuring it. The same expansion that will eventually silence every distant galaxy produced the brief, warm interval in which that silence has not yet arrived. That is where we are, inside the window, eyes open, while the light still reaches us,